this is where we left off last time. And again, I'm just going to re-emphasize, this exceptions topic probably isn't telling you much more than you were already aware of. Because it was the same thing in Python, and it's been the same idea in Java up until this point. It's just we never really formally talked about them. When something exceptional happens, it's not even necessarily a bug, it's just when something funny happens, we can throw or raise an exception. And then when that exception is thrown or raised, I'm using those words interchangeably. In Java, you throw exceptions. In Python, you raise exceptions. Same thing. You can catch the exceptions. And it's where you catch those exceptions that you can address the situation accordingly. Now, there are some type of exceptions that you probably don't go out of your way to catch, like an array index out of bounds. You're probably not going to catch those exceptions because that's just straight up a bug, probably. It's not so much an exceptional situation. You probably just messed up indexing that array. And null pointer exceptions can be like that too. But sometimes there are some cases where, well, I really do want to catch that exception and deal with it. If an exception is thrown and never caught, it keeps getting thrown to each calling function. So if I have a function, like my main called a method, called a method, called a method, called a method, that raised an exception, or threw an exception, and this didn't deal with it, 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 none of them caught it all the way up to main, and there's nothing that catches it main, that exception gets thrown at you, the programmer. And that's why you see index out of bounds exception, because it was never caught. That's why you see a variety of type null pointer exceptions. But we can catch exceptions. And this is important because if I'm writing the code in the year whatever, if I'm writing the code today and you're going to use my code tomorrow, I'm not going to know what you want to do tomorrow. And maybe every single one of you is going to be using my code tomorrow. And every single one of you is going to be using my code tomorrow for a different reason. And what you want to do in those exceptional situations will really depend on your situation. So there's no way I could know what you want to do. The best I can do is throw an exception that says something funny happened, and I can give that to you. And then you go, okay, I caught it. What am I going to do about it? So this is catching exceptions. We could stop immediately. Maybe you're running some code. Maybe it's some very important medical equipment or something. And you're running some methods and functions that do very important calculations to calculate the amount of therapy, like a quantity of some therapy to give to somebody. And if an exception is raised, suddenly I have no confidence in the quantity of that therapy that was going to be applied to the patient. So maybe that program, maybe it's a robot that's going to administer, I don't know. But if that happens, the program should stop immediately. Because if I can't guarantee, if something funny happened, and I can't guarantee that that calculation is correct, I might give him an overdose or something and kill him. So I'm going to stop immediately. And if something like that happens, I can catch the exception and do a system exit, which will just kill the program. It just stops it. So immediately stop if something happens. Maybe this is what we want to do. Now maybe that exception isn't really a big deal. Or maybe it kind of is a big deal, but your program really better continue operating either way. Maybe you're flying a helicopter and some exception happens. And the last thing you want is the software on your helicopter to just immediately stop in that situation. Maybe it just kind of ignores it and can carry on. So there we go. We print out the stack trace. The stack trace is what you see if you never caught an exception. Have you ever looked at the exception when you see like a null pointer exception? And it'll tell you null pointer exception line whatever. And then below that it'll have like another line and another line and another line. That's each method call that gets you to where you are. Because if method A calls method B that calls method C, and the exception is shown here, it shows you the stack trace. Where, like, because the methods, you can kind of think of them being like, you know, method A never finished, but it called method B, and method B needs to finish before method A can finish, but method B called method C, and then that finishes so B can resume, and you can think of it as a stack. So here, we can just print out the stack trace, whatever. Sometimes, what we can do is catch an exception, and then kind of like repackage it to be thrown again to be handled somewhere else. We could do that. Why? Because, I mean, the point I'm making is you could do whatever you want. And that's kind of the point. You do whatever you need to do in your specific situation. Best we can do is throw an exception when the code we're writing is doing something funny. And the best the person using our code can do is catch the exception and deal with it accordingly to their needs when they're using it. It is possible that maybe you're running a chunk of code that might throw multiple different types of exceptions. Maybe it could be possible that your code can raise a no such element exception and an index out of bounds exception. And if it threw one type of exception, you should deal with it one way. And if it threw a different kind of exception, you need to handle that in a different way. And we could do this forever. Maybe the code you're running can run 100 different types of exceptions. Each one needs their own version of cleanup and dealing with. That can happen. And all you have to do is you can just chain all of these catch blocks. You can kind of think of it as like an else if. You chain these catch blocks for each specific type of exception. You'll know like exception A, B, C, and whatnot. So if an exception B is thrown, well, the block, like line 6 is run. You'll also see a finally. A finally is like that, like else. After a chain of else ifs, you've got an else where, actually no, that's not right at all. A finally is what's going to happen no matter what. Ignore what I said about the else, that's entirely wrong. Finally, that code's going to run no matter what, and that's often helpful if you have some like cleanup code. Maybe you're doing some file I/O and a bunch of files need to be closed either way at the end of the day, whatever. Do note, however, that exceptions fall into the class hierarchy. Remember, everything is a subclass of an object. But under that, we have throwable, and under that, we have exception, and under that, we can have a runtime exception. We can also have I/O exceptions, and a subtype of an I/O exception is a file not found exception. So all file not found exceptions, this is just one particular example to highlight the importance of being aware of the class hierarchy with exceptions and how we order them. I actually believe IntelliJ does a good job at warning you if you put them out of order. But file not found exception is a subtype of an I/O exception. So if a file not found exception is thrown, a file not found exception is an I/O exception, meaning whatever's on line 5 would get run. But that might not really be what you want. Maybe what you want is, well, if it's a file not found exception, I want it to do A. And if it's just any other arbitrary I/O exception, I want it to do B. But the problem is, all file not found exceptions are I/O exceptions. The solution here is always start your exceptions with the most specific type to most general type at the bottom. The solution here is to just flip the order. If it sees a file not found exception, it'll deal with it. If it's not a file I/O exception, it'll go just to the I/O exception. So just be mindful of the order that you're catching them in, because it matters. Is that clear? Since file exceptions, yeah, whatever. And then finally, sometimes the dish has some code run regardless of the exception type that was thrown. Yeah. Any questions about exceptions? For the most part, that probably felt like a lot of review, and that is, yes, you're right. I will actually take a moment here. I meant to say this at the beginning of the lecture, but I'm just going to give you a bit of a heads up. So, this is not on topic with the course material, and really this isn't particularly relevant to you, because first of all, you're here, and what, like less than half the class is here right now, whatever. But I will just give you a bit of a heads up. If I am I'm going to say I, but really I'm just talking about like a professor in general, okay? Let's say I'm a professor who really cares about teaching, and I like teaching. When I'm lecturing, I look at your faces for feedback on what I'm lecturing about. So I can judge by like the looks on your faces, kind of like your body language, your level of engagement and everything, to kind of gauge how the lecture's going. Maybe the content's too easy, maybe it's too hard. Maybe that part didn't quite make sense, I need to go back and explain it a little bit more. Maybe I'm going too slow, I can speed up. All of these things I'm trying to figure out by gauging you. Okay? Now, I will say, and this is not just me saying this, this is a general theme a lot of professors have been kind of talking about over the last couple of years. We have found it is becoming increasingly difficult to do that because we don't really know why. My bet is it's a bit of like a screen face. You got used to like kind of like online learning, so you got used to just sitting in front of a screen, right? So when I look at you, I'm getting no signal. And that's not a criticism. It's fine. You don't have to tell me anything. But that means I can't like dynamically adjust how like what I'm lecturing. I can't take that to see how things are going, and maybe I need to hit something more, circle back and whatnot. So if I'm lecturing, in every lecture I can kind of get feedback throughout the lecture, I've got a pretty good resolution of how things are going. But when I'm really not getting that signal, I can only really look at like the tests, so like twice a semester to get a sense of how things are going. So, I don't know, try to, I don't know what it is. I'm not even giving you any advice. I don't know what it is. I'm just giving you a warning. And this is kind of like a general theme a lot of professors have kind of brought up. It's not a criticism. It's just more about like, it's a lot harder now to kind of dynamically change how the lecture is going because you can't really, and I'm willing to bet half of the problem too is, you know, the masks, right? So I can't really tell. But I'm just FYI, I don't know. Be more animated. I don't know. Help me out. Does that make sense? Do you kind of know what I mean, right? Who knows why it's happening, whatever, but whatever. All right. Okay, back on topic. Memory and the call stack. Just mention the call stack. I will also say, for the purpose of this topic, basically everything I'm going to say has an asterisk attached to it. I'm kind of talking about how these things work in an ideal, theoretical way. In practice, there's a lot of like neat tricks and whatnot that are done where if there was like some asshole in the room when I'm lecturing, they could be like, well, technically it really works like, yeah, shut up, I know. I get it, but it's not going to be helpful for this discussion. So I'm just going to give you a warning that this is going to be fairly high level. There might be some impreciseness, but that's by design. The preciseness is not important for this topic. If you really care and you want to learn more, by all means, geek out about that all you want. But just be warned that it is going to be a little high level. All right? So, programs use, yes?
Is this the stuff that's going to be covered in assignment 4, or no?
this particular thing? Assignment 4. I can't remember if there's, not directly, but, so assignment 4 makes use of, I think, recursion, which is the next topic, but this leads into that topic. And trees, which is the next topic. And several subsequent topics after that. Yeah. All right. So programs, so you gotta understand a little bit of the breakdown of your computer. All right? We have these machines in front of us, and we interact with them at a very abstract level. We've got a keyboard and a mouse and a monitor to like interface with it, right? But really, we've got, very simply, we have like a processor, right? That's the thing doing all the number crunching, all right? We might have like a GPU, oh, okay. A graphics processing unit, right? That's for like doing any like number crunching for like graphics and anything visual. And the reason these are standalone is because, well, a lot of the graphics that could be taking place on the computer now is fairly sophisticated. It could be done here, but it's often nice to have a dedicated processing unit for that. We also have RAM, right? Random access memory. Memory is just where we put stuff that we're dealing with. And then we have like some form of long-term storage as well. Let's call that like a hard drive, but everyone has solid state drives, but whatever, let's just go with HDD.
A lot of modern computers have SSDs, solid state drives.
Yeah, I literally just said that. Thanks though. So, these are all connected with a bus. And the bus is kind of like where all the communication happens, okay? This is kind of the general idea. For this discussion, we can entirely ignore the GPU. Not important right now. Here's what's going to happen. This is, let's say you're baking a cake. I'm going to draw some analogies. Hard drive, that's like your fridge and pantry, okay? That's where you're going to have everything stored. This is your countertop, RAM. This is where you put the stuff that you're actively working with. The processor is you, okay? You're manipulating the things to make the cake. And if you're using like a mixing machine, okay, fine, that's part of it, whatever. But this is kind of how it works, right? I load up things from my pantry and fridge, get all my ingredients, put them down on my counter, RAM. And the RAM is nice because it gives me a little bit quicker access to the things that I'm working with to do what I need to do to bake a cake. The bigger the counter space I have, it's a little bit nicer. Maybe I could put more ingredients there. If I have too small of a counter, who here has an annoyingly small counter where they live? A couple people, right? So do you find yourself having to make multiple trips to the fridge when you could have just brought everything out, but no, you have to kind of like be careful. Same idea, depending on how much counter space, how much RAM you have, whatever. But if we have a lot of RAM, a nice big counter, we're working away. So there's the idea. But you'll notice, we just got this like RAM, okay? And honestly, for the rest of this discussion, we really can get rid of this as well. Don't really care about the hard drive. There we are. Your program, when it's running, all of the instructions are ultimately being executed on this, the CPU. But the instructions for your program are stored in RAM. And your CPU will know, like, instruction, okay, execute that chunk of RAM, then that chunk of RAM, and then that chunk of, because where all the instructions are. But also the data in for your program is also stored in RAM. We have a shared RAM space. So, typically, instructions and data are physically stored. And if you're having a hard time kind of wrapping your head around, like, when I say physically stored, there's physical RAM. There's chips on your computer. That is RAM. And although there's a buttload of transistors in there, they're all storing like a low voltage or a high voltage that ultimately gets decoded to a 0 or 1 that ultimately means something to your computer. So there's physical differences in how the RAM is going to be configured depending on the instructions and the data. So this is physically stored somehow. Okay? All of this has to ultimately get represented in a physical world. So the instructions and data are physically stored in the same address space. And this is called the von Neumann model. Von Neumann, a very important mathematician and computer scientist. This is the von Neumann model. And there's a lot of reasons, there's a lot of problems with this model. Having a shared space can be very problematic, but we abstractly pretend they're different spaces, so it's fine. And there's a very important, noteworthy, historically alternative called the Harvard architecture that actually has separate chunks of RAM, like physically separated for instructions and data. And there's some advantages there as well, but we use the von Neumann model in all of your things. Point here too, to take away, is the way that we build these computers is uniform, like they all have the same general design. The components can be different, but the same general design is the same. But that design is kind of, I don't want to say arbitrary. It's not arbitrary, it's well thought out. But it's not like that is the design. The way that they are built and the way that they work is an engineering decision, not an ultimate truth of the universe. It's not like it has to be done this way. So just interesting note there. But having common memory address space for instructions and data could be a recipe for disaster, but however, modern computers have strategies for like mitigating potential issues, and many programming languages like Java included logically separated. So even though the instructions and data are physically stored in the same chunk of RAM, we very elegantly pretend that they are separate. So it kind of eliminates all those issues anyways. In many programming languages, and this is where the asterisks start, we have chunks of RAM for the instructions for your program. That would be like the code in your methods, your classes. Interfaces as well, I guess. All of your code, there's chunk of RAM for your instructions. Then there is the dynamically allocated chunk of RAM. This is the memory that your program has access to at runtime. So now, if we didn't logically separate these things, there's no separation here. We could just do whatever the hell we want in RAM. Our programs can manipulate RAM however we want. We don't do that anymore because it's a terrible idea. We do this logical separation. But we have a second chunk of RAM that we say this is for the data that we're going to be using in our program. It's where we're going to store instances of objects. If I need to store 100 student objects, I'm going to set aside a chunk of RAM in that block of RAM for that dynamically allocated stuff for 100 students, okay? And then we have the program elements. This is what's actively happening. This is where the data and information is stored about what's actively happening in the program. So we have a chunk of RAM for all the instructions, like a recipe book. We have a chunk of RAM where we can work with stuff. And we have a chunk of RAM that has like all of the stuff that we're actively using and need access to in there. The separation between this and this is a little less obvious, and that's kind of, yeah, you're right. But the instructions and then data, and the data is kind of separated between what's actively being used and then like what they call like the heap space, which is a whole thing. All right, okay. Memory allocation. Memory is broken down into two broad sections. The stack. We've talked about stacks before, and interestingly enough, it's the same idea. The same abstract idea, the stack. It's a stack. Obviously, it's not implemented in Java. It's a stack in RAM or whatever the hell that means. But there's the stack. This is where the information about the current methods being run is stored. These are like local variables for that method or function. This is the formal param. These are the parameters also, so like more variable stuff for the functions, methods, whatever. And also a return address, because it's interesting. You gotta figure, when you write a method that has a return at the end, or whatever, even if you don't have a return, there kind of is a return that just returns to the calling method. Remember, if method A calls method B, and method A finishes, where does it go back? Right where it left off in method A, right? But you've never probably really thought, how did it know how to go back there? Well, because, you know, Java stored the return address of where the hell it was somewhere. And it was in the stack. And then there's the heap. Been broken down further into the static space. That is like your program code, like I was talking about a moment ago. And then the instance information, this is that like dynamically allocated things like your objects and instances of stuff. Okay? Don't be too, this is how we can think of it. In Java, if we really wanted, this actually can be broken down further, but we're not going to play that game. Here's how you can kind of think of it. I'm going to zoom out a bit so you can see. We have the stack space. Then we have like the heap. This is where the objects in the heap are. And then we also have the static space. So the blue chunk is where all the instructions are stored. The top part, that's what's actively happening. If you've got a method, if you've got a main method running and you've got a couple variables in here, that's where it's stored. But as soon as your method needs to create an instance of an object, that object gets created in that heap part, that instance part of the heap. And a reference to it is stored as a local variable in the stack part. Right? Remember how like everything is a reference variable? Yeah. The reference variables can be easily stored in the stack part of RAM because it doesn't care about how big. Each reference variable is like the same size, but every object could be a different size from one another. An object for like a student object versus a priority queue. Priority queue is going to be a heck of a lot bigger than like a student object, right? Well, the Java will go and dynamically allocate how much RAM it needs for each object, but it can store the reference variable in the stack to tell you where to find it in the heap. Any questions about this? So this figure here gives kind of like a little rough idea about what I mean. And take a moment and look at it. We're going to talk more detail about like the stack part because it's very important. But kind of get a sense that each of those like yellow blocks is some object, let's say. And each of the green arrows, well, those represent the reference variables to those objects that are stored somewhere in the stack. Except you see the one in that big block? That would be an example of an instance of an object that also had a reference variable to another object. That's how you'd kind of deal with it. All right. Right, okay, so here's the example. For example, if I make a bag reference variable called myBag equals new array sorted bag. The information on what an array sorted bag is stored in the static area of the heap, that blue part. That's the instructions. That's the definition of everything in our code, right? Because it's the code, the instructions that defined the bag stuff. The instance of the array sorted bag is created and put in the dynamically allocated instance part of the heap, that big chunk in the middle in that figure. But the reference variable my bag is stored in the stack part. It'll be stored in whatever method it existed in. The call stack, so this is the stack. And we just talked about this in the last topic when I said that stack trace thing, right? If your program throws an exception, it'll tell you every method all the way to main and where the issue happened. Main's at the bottom, then called method A, method B, method C, method D, method E, that threw an exception. And the stack trace shows you all of those. In every line of code, that was the call to every subsequent method. The call stack is the part of memory where we store what's currently going on. And at the top of the stack is the current method that's actively running. The thing right below the top of the stack would be like the method that was running, but stopped running because it called the method that's on the top. So if I have main, the top of the stack is main. And maybe there's only one main method and it doesn't call anything else, whatever, it's done. But maybe your main called some static function. Okay, so the main's at the bottom of the stack and the static function gets put on top. In what we call frames, but we get there in a second. Yeah, okay, along with the other methods run, the call stack is also a stack. Pop and push and pop information to from the stack at one end. People operate on a mental stack throughout their everyday lives. Have you ever really thought, maybe you've never really thought about it, but I'm willing to bet you've done it, where you're doing some task, right? And you think, uh-oh, you know what? I need to go do this other thing. So you stop that task, and then you go do that other thing. And then maybe in the middle of that other thing, someone gives you a call. Oh, okay, well, pause that. I'll go on the phone. Then when you're done on the phone, you return to what you were doing, and then when you're done that thing, you can go back and do what you were originally doing. That's a stack, right? You've got this mental stack, right? You all have it, you've all been using it, you just probably never really thought of it like this. And not many people do. Computer scientists are weird. But we do operate like this. Now that I've said it, can you kind of think back and be like, yeah, okay, totally, I get it. Yeah, I've done that. Yeah, I'm seeing like everyone kind of, yep, absolutely. And this is you've probably done this in like debugging, right? You're debugging some problem A. And then when working to fix problem A, you discover that, well, you know what? In order to solve A, I need to fix the problem B. A new problem I found, but I got to fix B before I can fix A. And then when working on problem B, you realize that, really the root cause of the problem is problem C. So you go and fix problem C, and now that problem C is fixed, you can go back and just get problem B working just nicely, solve that issue, then go back to problem A and finally address it. Right? Debugging often happens like a stack like that, but we like to keep our stacks small by, encapsulating our code nicely, nice simple functions and whatnot. We test them so we don't have to go digging for a deep issue and untested methods that we're using. Anyways, call frames. Each time a new method or function starts running, a call frame is created. These are the things that actually get added to the stack. And a call frame will store a couple pieces of important information. It stores any variables that are relevant to it, so primitive type variables. It'll store reference variables to objects that it needs. It'll store the parameters that the method got, so just more variable stuff. And it'll also know the return address of where the stack is an abstract idea that's ultimately encoded in RAM somehow. So in our stack, knowing the return address is important because when we want to pop, to know what the next, to know what the subsequent, the thing below it is, that top, we need to know where to return to in RAM. We need to know where the call frame is in RAM in order to make that the new top when we're popping a call frame when it's done. Cool? I want to be clear. After this lecture, I don't want you to have all of this memorized. That's not the important part. The important part is getting a sense of the call stack and how each method kind of calls another one. And then when a method is done, it can pop. And then maybe that method also calls another. So this call stack will be growing and shrinking throughout your program. That's the important takeaway. All right. So consider this chunk of code here. Main calls function 1, which calls function 2. So I've got main. And then main calls function 1. Okay, I create a call frame for function 1, put it on my stack. Function 1 calls function 2. All right, create a call frame for function 2, put it on the stack. Function 2 calls function 4. Create a call frame for function 4, put it on the stack. Function 4 finishes, it gets popped. We return to the memory address, so that would basically be to function 2. Function 2 finishes, it returns to function 1. Function 1 continues, it now calls function 3, create a call frame for function 3, push it on the stack, function 3 finishes, pop, function 2 finishes, pop, function 1, or pardon me, 3, then 1 finishes, then main finishes, and the program's done. When that stack is empty, when the main method finishes and it's popped off the stack, the program's done. Here's how you can think of it. Like that. Start with main, called function 1, which called function 2, which called function 4, which finishes, which finishes, which calls function 3, which finishes, which finishes, which finishes, program's done. That's the idea. Understand the idea of the call stack. You can keep it very abstract, but each method that gets called gets thrown into a stack. The heap, very broadly speaking, can be broken down into the static space and the instance space. The static space contains one copy of all the classes, static methods, static variables, interfaces. And the instance space is where we store the objects that we've created at runtime. Runtime meaning, well, that chunk of code that ran said, go make a new array indexed bag that went and got created and ran, and we had a reference to it. Garbage collection happens, so we've got all of this space in that heap for dynamically allocated stuff. But it is a finite amount of space. So when a method finishes running and the call frame, when a method finishes running and the call frame from the call stack is not needed anymore, the memory is deallocated for us. It's dealt with there. When an object in the instance space is not needed anymore, garbage collection comes into play. So the call stack kind of manages its own memory. The heap space doesn't. The heap space, we created it in an instance. In some programming languages, when we didn't need it anymore, we'd have to go and tell the computer, that chunk of RAM that I allocated, I don't want it anymore. Delete it. Now, when you delete anything, it doesn't actually go through and set all the transistors to 0 or something. All it says is, okay, that chunk of memory, it can be overwritten later. So it doesn't actually go through and wipe anything. In some programming languages, you need to go delete these manually. And if you don't, you create a memory leak. You've got leaky code. in Java and most modern programming languages, they come with garbage collection built in. Meaning, there's another like program running alongside your program that keeps an eye on that instance chunk of the heap. That says, okay, maybe we're running out of room. There's a finite amount of room there, and maybe I'm kind of running low on the room. But, you know, I see a couple of objects in there that have no reference variables to them anymore. Meaning no one can get there anymore. So the garbage collector can come along and deallocate that RAM. The takeaway here is the stack kind of manages its own memory. The heap doesn't, but we have a garbage collector that will come along and look for things in that chunk of RAM, that heap, that instance chunk of RAM, that could fill up and we could run out of room. But the garbage collector observes for any objects in there that are not needed anymore, and it'll delete it for you. So it'll deallocate that memory, it'll free up the memory for you. Now there's a lot of rules and there's a whole system involved in how Java's garbage collector works that we're not going to get into. But the key here is, as soon as we lose reference to an object, you can never get to it anymore. So it's effectively useless. So it's eligible for the garbage collector to come along and get rid of it. Garbage collector might never need to because there was no issue with the RAM running out of room, but that's where it would come into play. So for example, if I deleted the reference variable head to this linked structure here, the garbage collector would be like, well, okay, this linked structure is now eligible for being removed because you can't get to it anymore. In the above example, okay, head, each node's next field, yeah. There are also references to, yeah, okay. Yeah, I just said all that. What would happen? Imagine in my main, I called this function right here, uh-oh. Knowing what you just learned about the call stack, right? Every time a new method gets created, it gets pushed onto the stack, and when the method finishes, it gets popped from the stack. Knowing what you know, what would happen here? If you call this function. A never-ending loop. Main calls uh-oh. All right, so what does uh-oh do? Well, it needs to print out we and then call uh-oh. And then once that uh-oh that it just calls finishes, I'm done. But I'm not done until that uh-oh on line 3 that I'm about to call finishes. So we'll go into that uh-oh. Oh, what does that code do? Well, it prints out we and it calls uh-oh. And it'll be done once that call to uh-oh finishes, so we just need to go finish that. So go into that method, and then we call, so we call uh-oh, we print out 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 we, and it's never going to end. We would just keep pushing all these uh-ohs onto the call stack. And this creates a very famous type of problem. Who can name that problem? StackOverflow.com. Well, the problem is just called Stack Overflow. That is where Stack Overflow got its name from. But this creates a stack overflow, meaning we kept pushing to that stack, never popped. We got a problem. But don't worry, you can finesse it so this doesn't become a problem, but that's a topic for next time, where we hit recursion. What time is it? Oh boy, all right, yeah, done.